Number 10 is asking the protons marked in red are, they could be homotopic, enantiotopic, diastereotopic, or heterotopic. There's two ways to approach this. One thing that you can do, replace each H with something else. If we call this D and then that's H, and you look at that, so what we can do is we can actually redraw this, and then also we can do that to the other. If you do that, we are producing two structures that are identical, right? They're absolutely identical. They're just different conformations. If you rotate this carbon-carbon bond, you can get from this to that. And the reason that you can do that is because there are two identical protons there. We're just rotating it. You get the same thing. If you do this test and you produce two structures that are the same thing, it's homotopic. So the answer here is A. To clarify what these other ones mean, right, you get different things. So enantiotopic, if you do this, you produce two enantiomers. If you produce two different diastereomers, you get diastereotopic, etc. And so that depends on the identity of what these other things are. This example is so simple because they're all protons here. If you start replacing protons with other substituents, you can be producing enantiomers and diastereomers, and so that would give you this different relationship between these two protons. But here, you replace one with D, the other with D, you get the same thing, homotopic. And we can also tell because of the symmetry of the molecule here. When you have this kind of internal symmetry, that is what designates these as being homotopic, which would not work if these protons, you start swapping them out for other groups. But in this case, very simple molecule, so those are homotopic A.